Welcome to this Myths and Misunderstanding about laser technology. Today we're going to deal with a subject that everybody wants to do as soon as they get their laser machine. I was no exception. 7 years ago, when I bought my first laser machine, it was a bit of a pile of junk. First of all, the tube didn't work properly, and secondly, the mechanics were a bit So after a couple of months I got that sorted, and then I desperately wanted to do photo engraving, and I created several piles of charcoal. We'll pop into the office shortly and I'll just show you one or two examples of my early attempts. Just a few seconds, because I don't want to labour on it too much. But what it does remind me is that a few days ago I woke up and I thought, do you know what? I'm going to pack my javelin and my discus and my running shoes, and I'm going to rock up to the Olympics. How hard can it be? Look, I've got all the right equipment. Delusional, I think, is the word you're looking for. But it's a good example of what we're going to be talking about today. You can't just rock up to the photo engraving Olympics with a copy of LightBurn under your arm. It's not that simple. Now, don't get me wrong, LightBurn is a fantastic piece of software. I was involved in taking some of the bugs out of it at an early stage, so I understand exactly how it works. But the time I did that, I had a little bit of an understanding of how digital graphics worked. When I first started out as an engineer, I had no notion of what digital graphics were all about. With the aid of some help from a graphics designer who explained to me the secrets of what digital graphics was all about, I was able to advance forward and change my piles of charcoal into something that got better and better. But as I learnt more, I improved more. But that improvement was all based on having an understanding of what the goal was. Until I understood what digital graphics were, I didn't really understand what the goal was that I was trying to achieve. Yeah, they were sort of okay results, but they weren't, they weren't saleable really. Now, LightBurn is an amazing piece of software. 110 out of 100%. You can't fault it. And it's continuing to develop into something which is becoming world-beating. But the sad thing is, although it's got many professional graphics tools in it, LightBurn in itself does not teach you anything about graphics. You use the tools and find that they don't do quite what you expect. But that's because you don't understand the philosophy behind digital graphics. So today I want to share with you the background to digital graphics, in the hope that if you understand more about digital graphics, you will make your pictures better. Now, the one thing I'm going to finish up with is the fact that you don't have to spend time with LightBurn or any other software to prepare your photographs for lasering. Preparing your photographs for lasering means you don't understand your machine, you don't understand the technology. Now, that's not meaning to be rude, that's just a fact. And I hope that by the time I get to the end of this session, you'll understand why I'm saying that. Many years ago, I used to do exactly that. Lighten my pictures, sharpen my pictures, do all sorts of things to my pictures to make them half presentable. Yeah, they were okay, but they weren't photo replication. They were image engraving, cartoons, with all the detail and all the subtleties missing that are in a photograph. Now, I came out into the workshop here to try and dig up some of my early work. I think I've thrown it on the bonfire because it was that good. We're into the office and we're going to start from square one and try and explain little by little what's involved with digital graphics, how you understand, can you achieve that with your machine? Can you achieve it with a certain material? What lens do you need? The secrets of what's really behind photo engraving. Here are the first few topics that we're going to cover. What you're looking at there is my monitor. And as you can clearly see, it's a white background with black letters on it. How does that monitor work? It's basically a 2D digital image, just like your photographs are 2D digital images. First of all, let me take you in closer to this screen. You can see that there are thousands of little teeny weeny square lights, thousands of little LEDs. The black writing is non-illuminated little squares, and the other ones are illuminated. Those squares are pixels on the screen. Now, without the aid of the magnifying glass, you can't see the pixels on that screen. And that's the whole point of digital graphics. It is a mechanism by which your eye is being fooled. You do not have the capability in your eye to focus down to a small enough point to see those individual pixels. That is the whole trick behind digital graphics. Fooling your eye. Your eye is very good at averaging things out. You've got black pixels and you've got white pixels. You can't see the pixels, you can only see the average of what those black and white pixels are creating for you. That's what your eye sees. How do those pixels work? Well, as it says on here, this is a 2D bitmap. Look, I've just dropped into an Excel spreadsheet there, and I think everybody understands how a spreadsheet works. You define each one of these little squares by its column identification and its row identification. That's a bitmap. It's as pure and simple as that. Your screen here has got thousands of numbers down the side and thousands of numbers across the top, hidden in the frame somewhere. They're not real numbers, but they're addresses, which allow the computer that's running that screen to say, I want that square there to be white. I want this square here to be red and the one beside it to be red, and all these others. So every one of these squares that's red has been addressed in the bitmap to present information at those particular coordinates. So that's what a 2D bitmap is, because each bit is mapped. Now, you could see these screen pixels because I've made them big. But here's an important point. The screen pixels are one size, but the image pixels, and let's regard that as being 1 pixel, is actually made up of 4 screen pixels. Screen pixels and image pixels do not have to be the same size. So what size is a pixel? That's a very, very interesting problem which you need to get to grips with, because pixels are the most important part of digital imagery. Now, I'm going to use this image for the next few minutes to illustrate some very, very important points about digital images. Now, what I've got here is the specification of what this picture is. It's the picture details. It says it's made up of 1.8 million pixels. And the picture width is 750 pixels wide and 839 pixels tall. Okay, but when it comes to picture size, it says it's 15 centimeters, which is about 6 inches wide and about 7 inches tall. But the important thing is there, the resolution, 127 pixels per inch. Now, you're going to ask me, what size is a pixel? Well, the answer is very simple, really. Look, it says pixels per inch. And we know that an inch is 25.4 millimeters. And if we divide that by 127 pixels per inch, we get a pixel size of 0.2 millimeters square. So we've got the same information here, and the reason why I want that there is because I want you to look at the number of pixels at the top there, which is 1.8 million, and here we've got a picture width of 15 centimeters, which is about 6 inches wide and 7 inches tall, roughly. Okay, resolution's 127. So you say, well, that's not a very high resolution, because I'm hearing people talk about 1000 dpi. Well, first of all, you must remember there's a difference between dpi, dots per inch, and ppi, which is pixels per inch. Pixels per inch are what you see on the screen and what's in the picture, and dpi is what dots you put down on your material. Now ideally you want dots to equal pixels, and that's really what all this digital image is about, making the dots match the pixels. But we'll come back to that subject later on. First of all, you've got to understand what a pixel is. Is it a fixed thing? Well, 127 pixels per inch. I'm going to change that now to 1 pixel per inch. So now, at 1 pixel per inch, my pixels are now 1 inch square. So what do you think is going to happen when I say OK? What's going to happen to that image? OK. Nothing. Let's look at the specification for that image again. Image size. And sure enough, look, it says 1 pixel per inch. But remember, it was 6 inches wide before. It's now 19 meters wide. The image hasn't changed on the screen, but the size of the picture in physical terms has grown massively. This is now a billboard that can be seen from half a mile away that looks exactly like that picture on the screen. That resolution. You've got the same number of pixels in there. Look, 1.8 million, 1.8 million. It's just a huge picture that can be seen like that from a mile away. Now, if you step up to the picture, those pixels will be 1 inch square. The pixel would define the size, the physical size of the picture, because it is what it says, pixels per inch. Okay, now let's look at this problem from another point of view. See that right eye there? Let's zoom in on that. If there's a big colour contrast, you can just about see the pixels down here. You can see roughly what the size of those pixels are. Just estimate how many pixels from where my arrow is up the left hand side of the eye to the right hand side of the eye. What should we say? 100 pixels? So if there's 100 pixels there, we could say that that eye is roughly 20 millimeters wide. So here we are back with a resolution of 127 pixels per inch. 0.2 pixels, remember. We've got a picture which is 6 inches wide, 15 centimeters. Why don't we change that to something like about 1 centimeter wide? Okay, we keep the ratio the same. Okay. Where's the eye gone? You can see the pixels because the pixels are now big in relation to the picture size. The pixels have not changed their dimension. The picture has shrunk and the pixels are there, not defining the detail anymore. There were 1.8 million pixels in the original one. We've now only got 8,000 pixels in this image. The pixel size is still the same. And this is really the important factor that you must understand about pixels. A small picture requires a very high resolution to see the detail in the picture. If you have a low resolution, like 127 pixels per inch, and a big picture, you don't notice the pixels are big, provided you stand far enough away so that your eye cannot detect the pixel size. Remember, this is all about fooling the eye. You need enough pixels to define the detail, or if you can't get the resolution that you want, you must make the picture bigger and stand away further. So we now understand what a pixel is. That image is 127 pixels per inch, making them 0.2 square. We can't print colour with our laser machine. The first thing we have to do with that picture is to change the image to get rid of the colour. And we do that by changing it to grayscale. Okay. The same number of pixels are there. The same bit mapping is there. But for every bit in the map, there's less data that the computer has to remember. Just like my wife jumps in the car, drives down the road and hasn't got a care about how it's working. She just drives it. That's how most people treat their laser machines. They expect the person that's designed it to have designed it perfectly to do what they imagine it will do. Imagination's a great thing. Sometimes when you lift the hood, especially on a Beetle, and find that there's no engine there, you'd be very puzzled. We are looking at pixels which are many shades of grey, which is why that's called a grayscale image. Now, the grayscale is something that was designed to suit digital photography and digital imagery. Black is represented by the number 0, and white is represented by the number 255. And I'm not going to explain how those numbers come about, but it's a very specific number that's used in computing. It's actually the number 256. So 1 to 255 is 255, plus the 0 is 256. So there's 256 shades in that image. Some people think that you can work with a grayscale image. Trust me, you can't. It doesn't produce a flat variable colour range just because you change the power of your laser. You dig deeper as well as burn darker if you change the power of the laser. So it's not photo engraving. It's halfway between 3D engraving in a very non-3D way. In general terms, steer clear of grayscale engraving. So there's another trick that we can now perform that somebody discovered, and that's called dithering. Now, this is the technique that they used for producing photographs on newspaper. This is a print industry technique. They only have black ink and white paper, but they can produce images that look like that. How? Well, let's go to a modification of this picture, mode, and we'll change it to something called a bitmap. Now, this is a bitmap already. It's a grayscale bitmap because all the bits are mapped and they're different coloured greys. But this is just called bitmap for convenience. Okay, now we can see over here that we've got a resolution of 127 pixels per inch. So we leave it like that, and we'll do something called a diffusion dither. Now, I'll talk about dithers later on. We say OK. Now look at that. It's sort of OK, but you can see that there are lots of dots in there. It's not very good, is it? But hang on, remember what I showed you earlier on? There are pixels on this screen and there are pixels on that picture. The pixels on that picture do not match the pixel pattern on the screen. There's a mismatch between the resolution of that picture and the resolution that's inherent in that screen. So if I change the size of that picture, let's just watch. No, 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 yes. I get to a certain size and the pixels on the screen match the dots that are in that picture. If I zoom in, and what we've got as we zoom in is just black and white. We haven't got any grey anymore. So when we scan across these patterns now, the laser is on, off when it's white, on when it's black, off, off, on, off, on. And that's what we're trying to do. We're trying to send a Morse code to switch the laser on and off to produce these pixel patterns. Okay, now these are just black pixels on a white background. So before we move on to the next section, we'll just sum up very quickly that pixels and pixel size are very important. You don't know whether that image you're looking at on the screen there is dithered or not dithered. It's a grayscale image. And it's not until I zoom right in that you can see it's only black and white. Now, the important thing there is the size of the single pixels. Now, I know there are lots of multiple pixels on there, pixel streams that are joined together, but there's also a large number of single pixels. Now, single pixels are the most important part of that picture because remember, your eye is looking for an average density of black and white. so that it can mix it into its own image of grey. There is no grey in that picture. It's only in your imagination. So if we change the ratio of black and white on that picture, you're going to finish up perceiving a different colour grey. And that's why the ratio of black and white in that picture is very important. There are no pixels in that picture that overlap. They're all individual pixels that maybe butt up against each other to make a stream of black or a stream of white pixels, but they do not overlap. You don't have the same luxury when you make dots. The dots that you make with your laser machine can be any size. You've got to make sure that the dots that you produce match the pixels that are on that screen. If you don't match the pixels and the dots, the ratio of black and white in your dotted image is different to the black and white ratio in that pixel image. And you're not going to be able to replicate it. That's the key. Making dots the same size as pixels. And if you can make dots the same size as pixels, you'll finish up with a result like that. Photo replication. Now, why can't you do that straight out the box? Well, the answer is because you don't know what size dots you can produce with your machine. It's not something you've ever considered. You just jump into LightBurn, fiddle with a few controls, and off you go. And you finish up with a pile of charcoal. Okay, so let's take a quick look at this little pattern here. It's a pattern that I have developed that helps me to set my focus and also to determine my dot size. The row of pixels, black, white along the bottom, are 0.1 square. In other words, they are designed for a 254 ppi resolution image. The row of dots along the middle are again 0.1 square, and across the top, dots that are 0.1 square that are joined together into dashes. Your lens is not the animal that you think it is. It's got its own mind, and it works completely different with a laser machine than if you were using a lens in a telescope, a microscope, or anything else that projects an image. We're not projecting images with our lenses. We're trying to focus power. That's a completely different way that lenses are used. So there's a lot more to producing a dot than just firing your laser beam through a lens. The lens is the means by which you focus the light, but it doesn't say all the light is being used to generate a black dot. Now, forget about all this stuff up here at the moment. Just concentrate on these few little dots down at the left-hand corner. Look at the white space in between the pixels. It isn't there. You've burnt it with a dot. You've covered up the white space. So there is your charcoal picture. But unfortunately, it gets worse than that, because dots are not the simple things that you imagine. Let's move up to here. And what we find is that a dot starts off at this edge of a pixel. And because the dot starts off at the edge of a pixel, half the dot is hanging off the edge of the pixel. The burn goes all the way across the pixel, and then when it gets to the other side of the pixel, it says, okay, turn the laser beam off now. But of course, by that time, the other half of the beam is hanging out the other side of the pixel. So actually what you've produced is a sausage-shaped burn, not a round burn. Okay, now, LightBurn is an amazing piece of software that tries to overcome this problem by allowing you to change the apparent dot size. Effectively what it's doing, it's reducing the thickness, the size of your pixel in this direction to try and allow this edge of the dot and that edge of the dot to come back closer to being more of a dot, as in down here. It can never do that if it reduces the pixel size to 0. Look, there's a 0 pixel there. You get nothing. LightBurn has to allow some width to the pixel, because if there is no pixel there, there'll be no dot. So that's the mechanism by which LightBurn is apparently changing your dot size. It's not changing the dot size at all. It's just changing the duration over which the dot is allowed to burn. So we can see here with our sausage shaped dot, if we've got a line of pixels like this, look what happens. We get a sausage burn on the left, sausage burn on the right, sausage burn on the left, sausage burn on the right. Look, these white sections here are actually sections that have been burnt twice with the same dot. Okay, so now not only have you got charcoal, you've got doubly charcoal. That's what happens when you get single pixels. What happens when you get multiple pixels in a line like this? Well, look, we've got our half a dot hanging out the left, half a dot hanging out the right, etc, etc. If we get double dots like this, look, we've still closed up the white space in between. The more dots we can combine together into dashes, the less effect this overburning on the ends will have. So I've demonstrated there what happens if you don't care at all what size dots you're producing, if you don't know what size dots you're producing. All you do is rely on a piece of software which hopefully prepares your image for laser engraving. So what does prepare your image for laser engraving mean? Okay, so here we are in LightBurn, the most amazing piece of software that was ever written. It's an upgrade from RDWorks, which was free. You pay a small amount of money for this and you get 1,000 times more usability and more tools. I can't sing its praises enough. It's a brilliant piece of software. But one of the amazing tools that's been provided in here that allows me to show you what's going on with dithering is this tool here. If we right click on the picture and go down to adjust image, we don't really want to adjust the image. If that image is good, and it certainly looks good, then why do you want to adjust it? You just want to print it with dots. The problem is, as we've already established, you don't know what size your dots are, and therefore the chances are your dots are bigger than this dreamy resolution that you think you're going to be able to print. 1000 dpi? 500 dpi? Who knows what you can print? What I've demonstrated to you is that a 0.2 dot is only good enough for doing a 127 ppi image. If you can get a 0.1 dot, you'll get a 254 ppi image. Very few opportunities exist with diode and CO2 machines to go beyond 254. Okay, now that lovely image there, I could ask you whether that is a grayscale image or a dithered image, and you would not know, because you just can't tell. The only way we're going to be able to tell is to zoom in on it and see, look, there are many shades of grey in there. That's not a black and white image. That is a proper grayscale image. The only way that they can be produced is if we change the way that our laser operates completely. Now, whether it's a diode laser, an RF laser, or a glass tube laser, the principle will remain the same. We change the configuration so that the laser remains on permanently. But what we do, we change the power of the laser per pixel. So we burn a different colour for every pixel depending on the power defined by the greyness of each pixel. And that seems phenomenal that we can zip backwards and forwards across an image and do that. The only way that you can achieve grayscale is if you're using an organic material that's capable of taking anything from a scorch, a very light brown scorch, to something that is reasonably dark. But of course, as soon as you try and produce something that is reasonably dark, what you're really doing is burning into the material. You're not scorching dark on the surface, because that's nearly impossible. You're digging into the material and producing 3D-ness to the image. 3D is a very bad way of trying to produce this image, because although it looks good on the screen, you won't be able to produce that in reality. Let me just show you something else about this image, the way in which it works. If we go to preview, there's the end result. Looks fantastic, doesn't it? Let's zoom in a little bit on that and see what's actually happening. Remember what I said to you, the power changes as we go across the image. Now we've zoomed in on the image, and what we've got there, we've got varying thickness lines, black through to white and grey and back to black. Those are the varying powers that are being sent to your laser tube to make it burn deeper or less deep, darker or less dark, according to this. But of course there's all sorts of problems associated with that, which I've dealt with in another myths and fallacies video, all about this matrix burning test that you can do. Go and have a look at it and you'll understand why grayscale is a very bad idea. You certainly can't get the definition into the picture. So don't even try and attempt to do photo engraving with grayscale. That's my advice. There's grayscale for you, and I've explained how grayscale works. Let's take a look at the next one down, which is threshold. Now threshold turns away from the grayscale principle and turns your laser machining back to an on-off system. You either turn it on or off. There's nothing in between. You can choose what the on power is. You can make on 20%, but off will always be 0, because white is 0. It turns your laser off automatically. Even if you've got minimum power set, you're wasting your time. The only thing that will take place now with the on-off system is maximum power and nothing. So the threshold system works on the on-off system. Okay. Now, at the moment, if we take a look down here, you'll see that we're set to grayscale. So this is grayscale on the left, and this is grayscale on the right. We've not done anything to it. So if we change this to one of the options, let's do threshold. So threshold has to make a decision based on the middle of the grayscale range. Is the image darker than 128 or lighter than 128? So this is going to finish up with a black and white image. And I'll just demonstrate that to you. Click. And there we go. Now, threshold is a very simple, what they call algorithm. Now, an algorithm is a little computer program which runs for every single pixel in that left-hand image. It takes a look at the first pixel at the top left-hand corner and it says, what colour is that pixel? Is it less than 128? If it is, I'm going to make it black. If it's more than 128, I'm going to make it white. And so it transposes the grey pixels into black and white pixels one by one as it scans backwards and forwards across the image. I mean, it happens in an instant because computers are so fast, but that is the mechanism that's taking place to change that grayscale picture into a binary black and white picture. Now, if we move down to this list here, you'll see that it says ordered, Atkinson, Dither, Stuckey, Jarvis, newsprint, halftone, sketch. Now, every one of those is an algorithm of different sorts. So there's a very large set of calculations that go on around every one of these pixels, looking left, right, backwards, forwards, before it makes a decision about what this should be. Should this be a black pixel or a white pixel, based on the area immediately around it. So every one of these dithers uses a different algorithm, a different set of parameters to decide whether that should be a black pixel or a white pixel. People ask me, what's the difference between all these algorithms, these different choices? Because you've got people that say Jarvis is the best, Atkinson's the best. I always use ordered. Any one of those three is perfect for photo engraving because you get the same result as the original. So if I could modify all of those pixels in that image to a round dot, the size that you put in your machine, that would give you a comparison to what the real picture is. LightBurn hasn't gone quite that far yet. He may do. Now, when I first started photo engraving, I thought that an image like that was a pretty good representation of that tiger. But no, it's a pretty good representation of a charred log. Okay, so let's now move down the list and see what ordered does. Click. There it is, ordered. That looks pretty damn good, doesn't it? Let's go and have a look closer and see what's actually happening. Whoa, whoa. What do we see there? It looks as though we've got black, white and mid-grey. How's that possible? Our machine can't produce mid-grey. When it's on, it's black, and when it's off, it's white. Where does the third colour come in? Well, I'm afraid the third colour comes in through your eyes because it isn't really there. So now we zoom in. What do you see? You only see black pixels and white pixels. We can do this on our machine. Black and white ink, remember, the principle behind all of this. The problem is, look at the number of white single pixels. All those white single pixels are going to get covered because of the black pixels that are next to them. Remember, every black pixel that you burn, if you can't burn it the same size as that pixel, you're going to cover over the white. And if you cover over the white, it ain't going to look like that. Okay, let's go down to the next one, which is Atkinson. Again, that looks pretty good, doesn't it? So we'll look at the eye as a good example. But then again, when we look down here, look at all these white little single white pixels. Now, single white pixels are the things that are going to get masked out by an oversized black dot. I mean, all this black here is not going to be worried because black over black is black. It's not going to matter. It's when we get to these little single dots here that we're going to cover them over. They're not going to exist because we're going to block them all out. Then we'll try dither. Ah, a completely different pattern. But look at the predominance of single black dots against single white dots there. There are patterns in there, but just imagine every one of those black vertical lines here, for example, look, every one of these black vertical lines here is going to get masked out because basically it's a black pixel, a white pixel, a black pixel, a white pixel. Just because they're vertical lines doesn't make it any difference. They're exactly the same as these single black pixel, white pixel, black pixel, white pixel patterns here. So again, we're going to produce a piece of charcoal. Now we'll go to Stucky and watch the pattern change again. Lots of single pixels, black pixels, which are going to mask the white beside them. Look at all these white pixels down here. I mean, there's thousands of them. They're all going to get missing. They're all going to get obliterated. Let's have a look at Jarvis. I mean, you know, you're going to see exactly the same problem again with Jarvis. All these white pixels are going to get masked out and obliterated. So let's take a look at newsprint. Ah, now here we go, something different. We've still got these pixels in here, look. We've still got single pixels, but what we've done now, we've agglomerated the pixels into a pattern. So yes, there will be some overlap of these blacks all the way around the outside of these whites, but you'll have a little bit of white in the middle. The bigger the white area, these black pixels here, look, they'll get half, 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 but you'll still have a chunk of white in the middle here. And all this white area here, well, it's not going to get masked out by these little black pixels that are going to be half hanging out the end. So you can see how newsprint is relatively, not exactly, but relatively immune to overburning of dots, single dots, because there are very few single dots in that image. And then we've got halftone. Oh, look at all the single dots in there. It's charcoal in the making, isn't it? Now look at sketch. It's a different approach to threshold, but it's nearly threshold. So if we zoom out, we should probably find that that looks much the same. It's a slightly finer detail. It's more of a pencil sketch, isn't it, than exactly what it says. It's a sketch. Whereas threshold was that. So if you can't produce, or you don't know what size dots you've got, the only way that you can deal with the inefficiencies or your inability to know what your machine is capable of doing is to prepare your image for lasering. Now, what does prepare your image for lasering mean? What I'm going to do, I'm going to show you now what preparing your image for lasering really means. So let's go back to one of these. Let's go back to the most popular one, which is Jarvis. Okay, let's move into Jarvis. And let's go back to the eye because it's a nice example to look at. Okay. And what we do the sort of things that people say. Well, first of all, you must change the contrast. Wow. What am I doing now? Look at the white that I've put in there. Now remember, the ratio of black and white is the thing that your eye detects to tell you the quality of the picture. And you are going to overburn all the single black pixels and encroach into the white area. You're going to reduce the white. So by modifying your picture like this, you're immediately reducing the number of black pixels and increasing the number of white pixels. So let's take the brightness up. And now look at the amount of white that we've got in there now. But what we are doing is changing the obliteration relativity in this area here. It's not going to get burnt out anymore. Okay, so we can change the gamma. What does the gamma do? Look, the gamma has changed, got rid of all these pixels now. So rather than burning them out, let's not burn them there at all. Now, anybody will tell you that preparing the picture for lasering means you need to increase the brightness. So you increase the brightness, and you can see what happens when you increase the brightness. You take away a lot of the black pixels, and you will leave single black pixels, which are going to overburn and fill in the excess white area that you've created. You're preparing your picture to overcome the weaknesses or your inability to understand what your machine is doing. Brightness is by far and away the biggest contributor to changing the pixel density. As you enhance it, you're removing lots of single black pixels and putting a lot more white into the image. You're changing the balance of the white-black ratio to accommodate the fact that you're going to be putting a lot more black into your picture than should naturally be there. And what we've got is a very light version of the original, which allows us to use bigger burns. But look, you can see that that is not a photograph. That is something else. It's not a sketch. It could be a charcoal sketch. It's a cartoon of the original. If the image is good enough to start with, don't mess with it. If you don't mess with it, you'll get what you see there on the screen. 1 pixel, 1 burnt dot. That's the secret of photo replication. I keep stressing that as opposed to photo engraving. We know that that image is 127 ppi. I demonstrated to you earlier in Photoshop what happens when you reduce the size of the picture. You reduce the size of the picture, which means there are less pixels defining each feature in the picture. It's a little bit of a false impression you get when you change the size in LightBurn. You might think that you're changing the size of your picture to fit your product. You are, and you're keeping the resolution the same, which makes perfect sense. Because just because you change the picture doesn't mean to say you can change the size of the burn that you can use for each dot in the picture. So the dots must remain the same size, 127 ppi. And what we do is zoom in on this eye. We'll set this to, it's already on Jarvis, and we will zoom in on the eye again. There's a huge number of pixels across the eye. First of all, let's close this down because we can't do two things at once. And we'll shrink this picture down. Okay? Now, the picture looks exactly the same as it did before. A nice, high quality, high resolution image. You can see everything you wish about the eye. And let's zoom in now. Do you see what I mean? We've reduced the size of the picture, and the picture on the screen looks as though you've not changed anything. But that's not the information that's going to go out to your machine. The information that's going to be sent to your machine is this information. These are still 0.2 pixels. They look bigger, but there's a lot less of them to define the quality of the eye. So as you reduce your picture, you will get a worse quality image. This is that strange relationship between picture size and resolution. Pixels remain the same size. There's just less of them for every object that's defined in your picture. So you're going to get a cruder picture. Now, not only are you going to get a cruder picture, but remember, each one of those dots is a white single dot, and there's more single white dots in there now than there was probably in the original picture. So you're just going to get a burnt mass. So what happens when we change the brightness? You're going to get a much cruder picture. If I make my picture bigger, and now that I've made my image bigger, look, I've got a lot more detail in the eye. Those pixels are still 0.2 pixels. I've just got a lot more of them. And because I've got a lot more of them, I get a lot more detail in my image. The other point that I mentioned, the bigger the picture, the less sensitive it is to resolution. Well, I hope I've driven the message home about the importance of understanding picture size and pixel size. They are related together. And the next problem that we're going to have to tackle in part 2 is how do you achieve a particular dot size to match the pixels? So you must understand what your machine is capable of before you can attempt to do photo replication.